Nuclear programs are constantly in the news, with reports that they're enriching uranium. Usually the stories mention percentages and centrifuges, but to the uninitiated, it's not clear why these things are important. What exactly does it mean to enrich uranium, and at what point should we be worried? Now, when I imagine enriching uranium, I picture teaching uranium to paint or dance or something, but I looked it up and that's not what it is. For nuclear power or weapons, the isotope of uranium we're after is U-235, which has 92 protons and 143 neutrons. But the vast majority of uranium we pull out of mines, 99.3% of it, is the isotope U-238, which has 3 more neutrons and behaves differently. Only about 0.7% of uranium in the world is U-235. U-235 is fissile, meaning all you need to do to split it is hit it with a low-energy thermal neutron. The neutron doesn't smash the nucleus apart, but instead is absorbed by the atom, making it unstable. When it splits, it releases energy and more neutrons that can then repeat the reaction with other U-235 atoms. You can still split U-238 atoms, but you need high-energy neutrons to do it, which is less efficient. So when it comes to producing energy, the higher concentration of U-235 relative to U-238, the easier it will be. Nuclear power plants that aim to produce energy steadily over a long period use pellets that are between about 3 to 5% U-235, while nuclear bombs that want to release a lot of energy all at once have concentrations as high as 90% U-235. The challenge is, how do you take naturally occurring uranium that's 0.7% U-235 and up its concentration to those lofty numbers? That's where enrichment comes in. A couple of approaches have been used to enrich uranium. The one used by the Manhattan Project to build the first atomic weapons was gaseous diffusion. In order to separate the uranium isotopes, the first step was to turn it into a gas by adding 6 fluorine atoms. Once gaseous, the uranium hexafluoride was pushed through membranes whose holes were just big enough to let the molecules through. The lighter U-235 moves slightly more quickly through the barriers, so after several hundred membranes, the gas at the other end had the required amount of U-235. The more modern method is using centrifuges, which are cylinders that spin at very high speeds, enough to separate the lighter U-235 from U-238. The first step is the same: turn all the uranium into gaseous uranium hexafluoride. Then, like a hipster with a vinyl collection, get spinning. As the gas is spun around, the heavier U-238 will move towards the outside of the cylinder, while the U-235 will drift towards the center. The slightly enriched gas there will be piped out and fed into another centrifuge, and on it goes, using thousands of centrifuges connected in series and parallel formations, steadily upping the amount of U-235 in the mix. Once uranium is 20% enriched, it's a simple matter of rearranging the centrifuges to create weapons-grade uranium very quickly. That's why a vital part of ensuring a country is only using their nuclear program for peaceful purposes is inspecting how their centrifuges are arranged. The proliferation of nuclear weapons remains one of the most serious threats to the world, but nuclear power's potential to provide energy without adding greenhouse gases to our atmosphere is a huge possible benefit for humanity. If we're going to use uranium for the good of us and the planet, then it just needs a little enrichment. While the centrifuges enrich uranium, they're also feeding the more concentrated U-238 the opposite direction, producing depleted uranium at the other end. Nuclear power is still something that worries a lot of people, and recently Russia decided to turn a boat into a floating power plant. To see if this is a bad idea, check out my video on it here. If you like this video, let us know in the comments below. Make sure to subscribe to Seeker, and thanks for watching.